And then I'm very pleased to introduce you today to our speaker, Puya Pakshad. And before I give the mic to him, I just want to read a little intro. So he is an IT PhD student at Illinois Tech. His research focuses on software security and AI-based approaches to bug discovery. He holds a bachelor's degree in computer software engineering from Arak University and a master's degree in the same field from Beheshti University, Tehran, Iran. He's passionate about developing innovative solutions to improve techniques used throughout the vulnerability lifecycle from detection to assessment. He's recently published multiple research chapters and papers, including work on refining the CVSS scoring system for more accurate vulnerability assessment. And then without further ado, I'll hand it off.
Thank you so much. Hello, everyone. Hello? Can you hear me? Yeah? Okay. Yeah, my name is Puya. I'm a PhD student or PhD candidate in ITM department, Illinois Tech University in Chicago. So I joined in IIT in 22. Before that, I just got on master. And I remember that time I was like a student that really like to work on the software security to see, okay, we can have some source codes. Some developers can write the codes. Okay, how much these codes are secure, or someone can expose the information that they are behind of this, the logic of your applications, or they can steal your data or can have access or no. So I now today the thing that I have to present, you know, that first I want to have introductions about what is the software vulnerability, what is the software bugs, so quick, just have an investigation about different research tree in the vulnerabilities, software vulnerabilities. And then I would like to show you my published paper in 23, which is exactly about predicting the software vulnerabilities in the granularity or levels of the function level. I mean that in the function level findings. So the first slide talks about what is the software vulnerability. All the people know what is the bugs. Okay, once your computer doesn't work, so you are seeing that probably something is going wrong and doesn't work perfectly. So the software vulnerability is the weakness in the code or the flaw in the design. So every people knows that the development of the application, software development, is like the, you know, that you are following the direct methodology. Sometimes it is like, you know, gathering the stakeholders of the project, first talk, okay, we want to build up the applications. Then you will have another meeting to talk, okay, we need to analyze what functionalities, what non-functional requirement, what functional requirements your project has. Then you will design the project, you will make a diagram, you will analyze it again, sometimes iterationally based on the methodology that you have in your software projects. And then we'll you know, give all the documents to the developers. Hey, could you please write and implement this application? After several months, your application builds up and the people run and the user use it. And then they will see, okay, do you have the bugs? Okay, these bugs comes from which part? It's so important, which parts of the process that you had the mistakes. So specifically, based on the OSP standards, the bugs in the computers comes from 2 points. One in the source code, that this is the weakness happens by the developers. Another part that comes from the flaws in the designs. Once your designers, your analyzers, that they have the mistakes that happen just as like a mistake that happened during the talk between the managers, designers, and stakeholders of the projects, that probably they wanted to implement another functionality, but the designers think in another way, okay, just write other sentences, and the implementer also implement the same thing. So all the process was wrong from the first stage. So the examples of the software bugs, specifically that is like SQL injections, or buffer overflow, integer overflow, DDoS attacks, denial of service attacks, and some attacks like this. And why does it matter? So the first things, you know, that once your computers, your applications in your companies faces with the bugs, so you have basically two different impact. Your company faces two different impacts. One of them is the business impacts, and other is technical impacts. Business impacts, okay, your company is Google, okay, you have the lots of bugs. Some attackers exploit some data, the user data from your companies. So what happened for the Googles? So all the people think, okay, Google cannot make secure my information. This is the business impact that happened for the Google, unfortunately. And the technical impact is still the data, exposing the data or the business logic that happens. Or any damage to the reputation, risks to the safety in the critical system. The example that happened in these months is for the call technology service software, the ransom attacks that happened with the specific type of the vulnerability. It's the SharePoint vulnerabilities that happen, leading to the massive data theft and the systems shut down, unfortunately. So this is so important to finding and catching the bugs. And another slide also showing that how much having the developing and working on the tools that can find and catching the bugs is so important. Let's see these slides. So you can see that the trends of the lines showing the several bugs. It's going increasingly going up, starting from 2014 until the last year 2024. And there are the several. In this diagram, you can see that there are the different type of the bug: SQL injection, executes, code excesses, file inclusions, and the total of them is just going increasingly. And so it shows that every year we have several new bugs. However, the companies around the world that they are working to decrease the bugs, finding the bugs at this correct time, but there are still lots of bugs every day comes up, and unfortunately damage to the companies, to the governments, unfortunately, there's infrastructures, everything. And unfortunately, attackers are still a little bit faster than the security experts. And so that's why I'm just mentioning that all the global company needs to focus on finding developing or building the more robust and powerful vulnerability discovery tools, vulnerability detection tools, and vulnerability assessments. This slide also shows that how much it is so important. This concept is how much it is important. The CVSS is the Common Vulnerability Scoring System, shows that how much this vulnerability is important for us. We will range the vulnerabilities in the different we have a different systems, like in the qualitative approach, the people say, okay, it's like low, medium, high. In the quantitative approach, the people range the vulnerability from 0 until 10. So here, if consider that it is from 0 to 10, so we can see that the bugs with the highest severity, that they have a lots of frequency. In between 7, the score will be between 7 until 8, and some of those that their score is upper than 9. So this slide also shows that the hard bugs or critical bugs, that they are still among these vulnerabilities that make these diagrams going up. So what research problem these days we have in concepts of the vulnerability discovery? The first thing is that the most of the tools still, unfortunately, that they are struggling the accuracy and noise. You know that lots of applications says, okay, I'm proposing the tools that my tools is working very well and I can catch all the bugs and all the vulnerabilities. But once you are working in practice, you see, okay, lots of bugs. It is reporting that this is bugs, but it's not. Or it should to find some bugs, but it cannot. So the false positive or the false negative, unfortunately, they are still the problem discussed between the security experts once they are working security tools. Or the zero-day vulnerabilities. The zero-day Zero-day vulnerabilities is like the vulnerabilities that we don't have any patterns yet about. They are the new bugs. If you can find the new bugs, so it's very good because the bug, most of the applications just using the patterns, previous patterns of the bugs. For example, you know some patterns, you have some metrics for finding the bugs, okay? Then you will be finding some of those codes that they are malicious or have the same or similar patterns of the previous bugs that you have. So finding the zero-day vulnerability is also so important. Data quality and availability. So there are lots of, data sets for the bugs, for the software vulnerabilities, network vulnerabilities with lots of features, labels, but they are still not, adequate or enough, or they are not so accurate, unfortunately, yet. We have also lots of the things that they are so good, like the things that probably you can find in Kaggle websites or some stuff like that. And also the lack of explainability and also the scalability, that they are the research problems discussed these days for the in the field of software vulnerabilities. So I just want to take a look at of the related works, or the research tree, specifically what different paths we have once we are talking about the software vulnerabilities. The first way, in the traditional based ways, so it is a static analysis or the white box approach. The white box once you are talking about the white box, it means that you are examining the codes. You don't have any executions of the code. You are only have the source code available on your hand, and you want to find the ways or use the techniques to work on the source code of the applications. So the tools that can help you, that they are so traditional, it's a flow finder, CPP checks, or the racks that they can, find some malicious patterns inside the code and just give you some report as a warnings, specifically about the rats and also the CPP check. And their significant, important, notable papers that they are the things that Viega or another one that published in the 2007 or 2001. Another way for, another technique for investigating the bugs is dynamic analysis. Once you are using the black box approach, why do you think that it is black box? Do you have any ideas? Yes, please. Exactly. Don't know it is what it is doing, because you don't have any access to the source code. You are just you have the application like the exe files. You are just you are just using these applications. You cannot have access, okay, how many functions this source code have, how many functions or how many modules this application has. Just you have the source code, you have the applications, and you can run it and see the executions. So in these ways, also there are lots of tools like the OS Zaps or the address sanitizers, ASAN, and also lots of applications. Specifically, I will talk about that a little bit later, that there are some techniques that, have an overlap with the dynamic analysis, which we call it fuzzing. Fuzzing is also another technique. I will talk about that a little bit later, but it's also on the the engagement have an overlap with the dynamic analysis, because you don't have access to what is happening exactly inside the source code. What is the source code what is your source code? You can only run your applications based on several different inputs. For example, you can say, okay, I will run my computer with, for example, number 4. Second time, you will run it with the number 10. With different values, you can run your application to see, okay, based on which one of these values, my computer will have the crash. So they are really traditional. I just want to discuss it and, cover all the concepts. Hybrid ones is just combining the static and dynamics. It's just like, you know, that a little bit static means that you have access to the source code, and a little bit have the coverage about the dynamic means that you will have the running execution of your applications as well. And the notable papers that publish in the ICSE is 20,000 by Sharet al. And the fuzzing ways, the idea of that is that just, you know, automatically generate large amounts of malformed input to expose crashes, memory errors, and the security flaws. And the the famous tools in this ways is AFL Plus, LeafFuzzer, or the AFL Go. AFL Go, exactly, it is another, you know, a specific branch of the fuzzings. We call it directed gray box fuzzings. What does it mean? It means that you have partially access to the source code, the graphs of the source code. You know what parts of the applications are the targets for your malicious activities, or what part of the application is vulnerable. You want to generate the inputs that can follow the specific paths leads to reach to that targets. That's why we will call it directed gray box. Gray box, it means that it's white box and black box together, hybrid ones. Means that you have the access to the source code, and also you want to run something. What you want to run? You want to run your input. You want to, you know, generating the new inputs and feed it to the computers to see, okay, based on which inputs my computer will have the crash. That's the idea behind of the fuzzing ways. And the symbolic executions is another ways that mostly I will not see these days that the people use it because it has a lots of, you know, limitations. But the idea of that is execute code with symbolic inputs and builds logic constraints on program paths. Solving this construct produces test case like the inputs that explore deep execution paths. The challenge of the symbolic executions idea is that path explosion, constraint solving overhead, because you know that you need to make lots of symbols, and based on these symbols, you want to make a formula and give it to the solver to say, hey, I have several constraints, lots of symbols. Okay, now please solve my constraint by the solvers. And in several cases, you will face with the situation, the circumstances, okay, you have lots of different paths and you will face the path explosion. That's why this phase is a little bit time, it's not a little bit, a lot time consuming. But the popular tools in this phase is the KLEE that published in the 2008s. And the last traditional base are the patch differential analysis and the penetration testing, that which it is more, you know, popular in the industry. The penetration tester is also a job in the for the companies that some ethical hacker just wants to attack to discover exploitable vulnerabilities. Like you can use the several different applications, tools, or there are, you know, several companies like SaaS companies that you can register the courses there, go and learn, okay, how many tools we have for as a penetration tester. I can learn for, you know, make a report from the assets that your company has and give to your boss, for example, okay, I test these computers, these assets of the companies, and your companies, for example, these assets, this software, that network that have the, for example, 10 bugs or 5 bugs, and what is the severity of them. All these processes, these tools will do. And the popular tools in this phase, Metasploits, Burp Suites, which is so important, and the Nmap, Nessus, and the several other ones that, if you would like, we can discuss it about. After the traditional ways, so for vulnerability detection area, once the AI, you know, emerging, so it will just combine with the previous ways. So the new generation of the AI based, the early generations, the first branch of them is classification and clustering with metrics. What does it mean? You remember that we talked about static analysis, dynamic analysis, and the hybrid analysis. Okay, consider now we can use the machine learning's ways. So the machine learning can have different approach we can have once we are talking about the machine learning. You can see that this is you want to follow the supervised way or unsupervised way. You want to use the classification techniques or the clustering techniques. You have the labels on your data sets or you don't have any labels. And so these ways, specifically using some code metrics or the code patterns. And first, you can extract your metrics from the source code and then feed the data that you extract from the source code to the machine learning models, which is the ways that I used in 23 to publish my paper, which is the last paper here that I want to talk about that a little bit later. This paper. This is that it will be, put in this category. Another way is the text-based analysis. In these ways, the security experts treat with the source code like the natural language. It will, that we just see the codes like a text, like a message, and then we will tokenize all the identifiers, all the codes, and then feed all of the information we gathered, we tokenized to the NLP models, natural language models, or the other deep learning models that we have. And the papers that you can see that they are more interesting are listed here. Then another way is the tree-based analysis. It will, instead of the tokenization, we will first use the abstract syntax tree to parse the code with the abstract syntax tree to generate the abstract syntax tree. It's also like the tokenizing, but in another approach, and then learn the structure and the syntax pattern from the intermediate representation that we generate, which is the abstract syntax tree, AST, of the source code. And then we will give it to the machine learning models, neural network based, and we will have the expectation that, okay, now the machines have the better sense from the source code, and it can identify the vulnerable codes, vulnerable path, vulnerable functions, and some stuff like that. Another way, instead of watching the codes like the tree, we can see it like the graph. So in this way, we will convert the programs or the source code to the graph structures, CFG, DFG, or the CPG. So the CFG is like a control flow graph, data flow graph, or the newer one, which we call it code property graphs, which consists of the three graphs. The first one is abstract syntax tree, the second one is control flow graph, and the third one is data flow graph. I mean, that's a CPG combine all three graphs together as a one integrated graphs, and it is so reachable graph that I use on my published paper. And the CPG will be also published by the Yamaguchi in 2014. So another way for the AI-based in the graph-oriented ways is the GNN ways. The GNN models, it will try to learn the node and the edge of the graphs, embedding in the program graphs, and try to detect the vulnerability patterns. The last one of the classification method, it's like, the low level, working with the binary and multi-classes, try and train the classifiers to predict the vulnerability and also the vulnerability types. And the recent approach in the 2 years ago so far is the hybrid structural semantic using the large language models and the reinforcement anomaly detections. That the most important things these days is the papers working with the LLM based techniques, which use the large language models for the raw source code analysis. For example, this paper here, the Valberta, it doesn't use any IR, any intermediate representation. It will not use the graphs, trees, anything. It just see the codes like the token, like the message, make a tokenization from the source code. For example, if you have the, for example, int main, it will say, okay, int main, just like, the token of the codes. And then it will make a pre-builting with the one Robert, with the one of the LLM tools, LLM models, we call it Roberta, and then it will make a fine tunings on the Roberta with another machine learning algorithm and make a so reachable vulnerability framework tools. Okay, back to the paper that I told that I wanted to discuss it. This is my paper, a security vulnerability predictor based on the source code metrics that I published in 23. The ways that my approach based on the related work sections is this. I use the static analysis tools. Why? Because I just gathered the several source codes and have the access to the source code of the programs. And I used, that I converted the source code representation to the graph representation to the reachable, the most reachable, richer one, which is the code property graphs. And then I use the code property graphs for calculating several security metrics, specifically 15 security metrics. And then based on the metrics that I calculated for each function, so I had a classification. I used the classification methods to learn my data sets that I gathered as a machine learning models for predicting the vulnerability, and also 8 types of the vulnerability. I mean, not only the vulnerability exists in your code or no, but also several types of the vulnerability. Okay, for example, if this function is vulnerable, okay, the type of that is, for example, denial of services. This is the framework that I used. I first had the source code of the programs. We have, this architecture includes 4 different components. The first component is the code property graphs. First, I use the multi-stage parser to convert the codes to the graphs, and then I will store my graphs in one of the graph-based database, which is the Neo4j ones that I stored the graphs there. Then I wrote the traversal program with the Python language, and my codes do. My codes just that calculating 15 metrics that I will show you all the metrics in the next slides to calculate the 15 metrics per each function. Okay, what exactly I'm calculating for better understanding? Consider that the first row is representing one function of your programs. Per each function, I will calculate 15 metrics, numerical values for each functions. And then, based on one strategy that I used, for example, the first 4 metrics, just add up them together and put it in a same so for those functions that the add up of the first 4 metrics have the same value, they will be in the same categories. And then for the remains 11 ones, I will just add the value of the metrics together. For example, I start from metric 5, metric 6 until metric 11s. Metric 15s, I'm sorry. Just see, okay, which one of these metrics inside the same category has the highest value. With the 2 iteration, I just cut it to see, okay, which function has the highest vulnerability, and then put the 1 for those one. And then check with the ground truth to see, okay, does this function is really vulnerable or no? Consider that we already know that those functions are vulnerable or no. How we can check that this function is already vulnerable or no? We have the information of all these functions in some popular repository, security repositories, like, you know, uh, national vulnerability databases, we call it NVD, or common vulnerability exposure, like the CVE details website, that all of them handled by the NIST companies, I mean. And so far here, we have the data sets based on the, okay, what metrics we have, and also what is the results of them. And then based on those ones, that the results of really true means that those rows, means that function is really vulnerable. I just gathered manually the information of the what bugs it includes. How I gathered the types of the bugs from the CVE details or NVD websites. Then I just add another data set, like merging two data sets together. So as a conclusion, the first one was just calculating the metrics to find which rows are vulnerable. And then based on those ones that they are really vulnerable, in the real world, they are vulnerables, I just add the vulnerability type based on the 8 different types of the vulnerabilities. All the calculation here happened automatically using the Python codes that I wrote here, that I show you 2 slides later. And first, I gathered for my experimental result manually, but for the resting of the experimental, all of them happened automatically. After that, we had the data sets showing some features per each function, because every row is showing one function of your program. And also some types of the vulnerabilities. So I just gave it to the machine learning, to the 11 algorithms, different 11 machine learning algorithms that, okay, I will talk about that. So first, just for, wrapping up these parts, I think that I would love to show you the C code property graph first of all. So let's see, this is the graph representations of the, this is the code property graphs showing the abstract syntax tree. They are the abstract syntax tree based on every nodes. The green ones, the red ones showing the control flow graphs, and the blue ones here showing the data flow of your programs. This is the code property graphs. Then I just wrote the codes, for example, to, the calculating some metrics. How I did it, my codes just, traversing inside these source codes, inside this, into these graphs to calculate some metrics. What is the metrics? The first one is cyclomatic complexity, which is so popular that all the security experts using these metrics more than 20 years, I think. Another, number of loops. The metric tree is number of nested loops. How many loops we have in the code? This is the metrics. How many nested loops we have inside the functions, inside your source code? Or what is the maximum level of the for? I mean that how many for that you wrote inside together? Or number of the variables, functions, arguments. And metric 6, metric 7, metric 9, metric 10, metric, the highest level in nested controller structure, highest level in nested. I have a mistake here, I think. Yeah, just same together. I need to correct it. Metric 13, maximum data dependency. Metric 14, for example, metric 14 saying number of if structure without else. What, do we have anyone here can say why this metric is important? For example, you have the source codes, you are the developer in your companies, and you want to say, okay, do you have any functions in your source codes that in your function, you have several if structures, but your if structure doesn't follow any else structures. You have only the if structure. If something is true, for example, do something, but you don't have any else structures. Why it is important? Yes, Jeffrey. Exactly. It is still, remains the code's opens because you have the several other branches. In some scenarios, probably your codes based on some specific variables needs to go to the if, say, okay, we don't need to follow this if, and it's really necessary to have the else statements to handle that value. If you don't handle that value, this value goes in a little bit later and it will cause a crash. That's why the programmer is also sometimes using the try cache structures to handle. Let's think about that. If else is like a try cache as well. That's why this metric is one of the security metrics. If your code doesn't have this metric, so this is one of the, the signs of the vulnerability that probably this function would have some bugs and make a problem later than for us. So they are the security metrics. And I can show you first these slides. This is one of the, for example, the one part of the codes. First, we just use the, just make a connector with the join tools. This is the tools that you can use for making and generating the code property graphs. And also it's not only code property graph, lots of other graphs you can also generate with that one, like call graphs, abstract syntax tree, CFG. Separately, I mean that you can generate them. It depends on your research, your application, your projects. And for example, for the first metric that I told, complexity, the complexity, psychomatic complexity. So all the people knows that the psychomatic complexity calculated by differentiation of the number of the nodes in your graphs and number of minus number of the edges plus 2. So it is the formula of the complexity. So we can have the the query, writing the query with the gremlin. I just wrote these codes with the gremlin ones to write the codes with the gremlin language, and also another codes for the nodes ones to just trying to minus together. It's for the first ones, then the N ones for the nodes, the E ones, and the M ones, how it is calculating number of the edges minus number of the nodes plus 2 to calculate each metrics. Metric 1, metric M, metric 3. And yeah, someone from there told me that please announce that there is penalty of the pizza left. If some of us. It was a good thing for fun. Yeah. For wrapping up this part, so I can say, okay, I just calculated the data sets, merging with the types of the data sets per, per 15,181 functions, C++ functions. I gathered all of this information. I mean that I gathered all these metrics, 15 metrics, and those types. I mean that the cardinality of my data set was more than 15,000 rows, means gathering the information for 15,000 C++ functions. And their vulnerability types information gathered from the national vulnerability databases and the CVE details ones. And then using 11 machine learning algorithms like logistic regression, Connier, KNN, regression tree, naive Bayes, and among the all ones, the LSTMs has the best accuracy among the other ones. More than 83%, I think it was, for the vulnerability identification. Yes, please. I trained, exactly. I trained the data sets. I trained my data sets for, each types of the bugs separately to see, okay, can you please say me, based on, for example, this train data set and these test phases, you can say, could you please say me that this rows exactly, is it vulnerable or no? Or if it is vulnerable, what types of this vulnerability? So if you know that for example, if the types of the vulnerability would be buffer overflow, it should to show 1 for that one. Yes. Exactly. You can now have the access to the which type of the box it has. Not only did some malicious things is that, what type it is. Yes, it was the contribution of this paper. Thank you. And the result here shows for the more than 10 real world projects, open projects, the number of the vulnerable functions in the ground truth we had, for example, for the free type, libtiff, OpenSSL, 42, SQLite 10, bnautilus 84, open source 8, our desktop 6. Okay, I gathered these informations. This is the ground truth that we already knows that the number of the vulnerable function for free type, for example, 74. The previous papers before me, for example, the paper 12, it gathered the 56 ones of these 74. I gathered 64 ones. The 16 for the libtiff, my paper gathered the 17 ones. And you can see the comparison of the results here, which is interesting, I think. And based on, for the vulnerability types, we can see that based on these applications, these source codes, okay, how much that my frameworks was successful to detecting the denial of service ones, the code executions, overflow, memory corruptions, SQL injections, bypass, and gain sensitive information and gain privilege vulnerability. The columns ones are the types of the vulnerabilities. It was that paper. So for the the last parts of my presentations, this is the thing that you saw. It published in 23. Now I submitted another paper, which is a little bit, larger than, a little bit wider than only the vulnerability discovery in the source code levels, which is in the design levels. It means that we want to jumping back from the code to the design phase. If you remember, at the earliest time of my talk, I told you that in the companies, you will see that the people first gather together, talk, okay, what application we want to write, what application we want to implement. Then we will have the analyze phase, design phase, and implementation phase, test phase, different phase we have in the software companies. In most of these companies, I see that we will see that lots of times we don't see this good document or a specification of the projects. For example, your companies follow using some applications or third-party applications, but there is no any available or predict documents, any accurate documents about, okay, this application, for example, how many modules this application has. For example, what was the different alternative or the use cases for this? For example, if for example, the application needs to have the login modules, okay, what was exactly the scenario of that login? All the people only think, okay, login just needs to have the username of the password, or in the best case, just needs to, following the two-step verifications, sending some message to my phone, okay, what was the digits number, and enter it. But specific with the software mindset, in each companies, in each project, the characteristics of the project would be different from the other ones. And probably the logins also would have this different scenarios. So do you have to have the access to the specifications and the documents of your projects for in a future, probably you need to come back and have some modifications on your projects. So you need to have the documentation. You need to have access to a specification to see, okay, what things we wrote that time, for example, 5 years ago, 10 years ago, how we can modify it, how we can update that application, that systems. It could be the application of for example, the CTA in Chicago, anything it could be. So my approach is that I want to consider that we don't have any access to the documentation or a specification of the projects. Can we have the ways to coming back? We have only the source code of the application. We only know that, okay, this is the application of the, for example, CTA. This is the source code of the CTA. This is the source code of the CTA applications. Can we jumping back from the implementation phase to the design phase and regenerate again the documentation that we had before implementing? It's like, reverse engineering, jumping back. So my idea, again, follow this structure. It is a static analysis because I have access to some C++ source codes of the projects. The tools that I use, again, I will use the join tools to just generate these graphs automatically. I will have the, the low-level graph representation, but it is still low level. For the high levels in the software terms, we will have the lots of diagrams like use case diagrams, activity diagrams, data flow diagram, which is a little bit traditional ones, but it is still using, and also the sequence diagrams and the diagrams like this. And I just want to, first generate these diagrams. If we will be able to generate these diagrams, so we will have a lots of enhancement and advancement, because, this is the innovations. You have the source code and you are jumping back to see, okay, what was the diagrams of these source codes? All the people just follow the direct way from the design to the implementation. No one's coming back from the implementation to the design phase. The third phase is that consider that we will be successful for generating these diagrams. Can we see from the security aspects, the CIA confidentiality, integrity, availabilities, three, this is a triangle of the security that every security expert knows about. Can we see with the CIA concept, okay, what scenarios, what things should to be considered, already should to considered in the design phase, but we don't have it in the implementations. And yes, please. Confidentiality, integrity, and availability. Yeah. Integrity of the data, confidentiality, and the availability. Yeah. And this is the proposed architecture that I want to show you, that what exactly we are doing, because you know that it's on the submission process. It's okay, I can show that what is going on exactly. We have the source codes. We will extract the low-level graphs. Now we have the access to the source code and the metadata based on, that what is the abstract syntax tree for each source code? What is the control flow graph for each source code? I mean, once I'm talking about the source code, I mean each function of the source code. Consider that you have a function like int main hello world. Okay, what is the abstract syntax tree of that? What is the CFG? What is the DFG? What is the call graphs? And then we will store all of this information as the JSON with the JSON structures in the data sets. Then we will use the large language models and prompt engineering we will do to say, okay, hey, machine learning, could you please consider that what is the notations of every use cases or every control flow graphs, and then this is my information. Could you please generate the diagrams again? So on my experience and my colleagues in the lab office in Illinois Tech, we were able to generate these 4 documents with more than 90% accuracy. And then we will give this information to the large language models again and say, okay, now you have access to the diagrams of this source code, the design level of this diagram. This is the design level. This is the high level diagrams that only the business managers, the designers, the manager of the companies can understand and use these diagrams. Can you please, LLM, can you please generate the security policies that probably they violate during the drawing these diagrams? What security policies we can use? What is this, our ground truth here? It could be the ISO 27001, 2, 3, 4 until 13. It could be the NIC document. It could be the OS documents. And yeah, I would love that sometime later I can come back here to show the results after this paper will be accepted. And yeah, it was my presentation. Thank you so much for listening, and thank you so much. Yeah. Mhm. Yeah. I got you. Interesting. Very nice questions. Very nice questions. Actually, yeah. You know that you first mentioned about the history of the source code, right? So the history of the source code means that uh, can we see that do we have any patch in the past in the source code or no, right? In these projects, I didn't consider, but it's so interesting, and it's so interesting things that you told, that he is mentioning about, that considering the history of the vulnerability that occurred in the source codes as one of the metrics. It could be one of the metrics that if I had this idea in the 23, I added to the other, other metrics. But just one thing. But for this, the thing that you told is so important. If the people wants to make a using the large language models for making models for predicting the vulnerability, so they should to use this metric as well. I believe that it will make a more accuracy for vulnerability detection. Yes, please.